Is that clear? If I get the index here, the corresponding node number in this array would give me the node number. So that way I have reduced LCA problem to an RMQ problem. So we can have the same time complexity here, n log n pre-processing and order 1 query answer time. Why is the R array calculated? The R array is calculated to get the first index of my nodes I and j. If I am doing a query for nodes I and j, I use the R array to get the first index of I and j, and then I do a query in L array for those two indices. I have taken up a tree and then I have generated the E array for it, L array for it, and then R array for it. There is a query that is given which is 6, 9. So you do an RMQ on 10, 16, which are the corresponding arrays for 6 and 9, and you find that in this sequence 0 is the least number. The 10, 16 is 11. So this is the least number. The index of this number is 11. So you report this as E11, which is 5. Okay. There is actually also a way in which you can solve this RMQ problem in order n pre-processing and order 1 query time, but the constant factor for that solution is quite high. So in a contest-like environment, in a programming contest-like environment, the performance of both these solutions are almost similar. While the n log n solution is very easy to code, just a few lines of code, I just rubbed it off, but just a few lines of code, it is 3 to 4 lines of code. This one takes a hell lot of coding. So anyhow, if you want, you can go through this. This also exploits a very good concept, just for your interest, if you want. Okay, now we are coming back to this problem. We are given a tree. You can do any amount of pre-processing you want, but preferably as less as possible. We will be given queries of the form. Let's just take a first query. We are given queries of the form A, B. We have to report the length of the path between A and B. Can anyone come up with a solution now? Yeah.
Assume you have a path length stored for each node, stored from root to that node.
Okay. This is the level number, right?
Yeah, level number.
Yeah.
So length from root to that node plus length from root to the second node minus the path length between these two nodes and this LCA. I mean, whatever. Minus the path length between these two nodes.
Okay. Let me give you an example. If I am asking for the path length of path between E and H, it would be 1, 2 and 3. Okay? It passes through LCA.
Okay, sorry.
So
okay, from the first node to the root plus second node to the root,
okay,
minus twice LCA to the root.
Yeah. You just find out what is the LCA of A and B. Let's say that is C. So what we do is, I find out what is the length of this path. I find out what is the length of this path, and since we have counted this twice and this was not a part of our solution, so we subtract the length of this path. So what is this path? This part is the level number of E. This part is the level number of H. Now if we have C, this part is the level number of C. Does this make sense to everyone?
Yes.
Okay. So this way you can get the length of path between E and H, meaning any two nodes A and B, if you did LCA thing. Now how do you do that second part?
From the LCA between A and B,
okay,
we go down the number of levels till we reach K. Half times K.
Half times K, it not necessarily be half times, because this path length is 1, this path length is 2. So if I am asking you, or let's say this path length was 4, 3. So if I am asking you the second node, then this is my answer, right?
Yeah.
So how do you do that? What is your solution?
From node 1, from the root node, calculate the length up to node 1.
Okay.
And also calculate the length up to the LCA.
Okay. We'll get the length of the path between
if we subtract, we get the length of the path between the node 1 and the
LCA. Okay.
And then from the LCA, we need to calculate the kth node, right, on the path. So kth node must be, you have to calculate the node at level k minus this length from the LCA. So we add the level of the LCA to it and calculate the node from the root node to, we need to see the node.
There will be many nodes at that level, right? So which one? You'll be going down that path, right? So it will be order of k, right? Can you do anything better than that? So the solution that he suggests is, okay, let me first clarify on what he said. You can actually, if you have two nodes A and B, let's say this is A, this is B, this is a little hodgepodge, but if you can make that out, let's say if this is A and this is B, then you can find out what is the LCA of A and B, right? The LCA could be found out. You also know the level number of LCA, right?
Yeah.
So this way now you can find out what is the path length between this and what is the path length between this. If k is less than this path length, then k lies here, somewhere here. If k is greater than that, then k lies somewhere here, right? So now my query becomes that once I know which part it lies in, so my query becomes that what is the kth node on my path from this node to the root, right? If I know that, okay, this is the, let's say my k lies here, so I want to know what is the kth node when I travel from this to root. Is that right? So to do that, what I do is I do a pre-processing. For every node, I store what is the node which occurs at a distance of 2 power j from that node. Okay? Same way as we did in RMQ. For every node, we store what is the node that occurs at a distance of 2 power j from that, where j can take all values which are possible. So now when you are searching for the kth node, you look at the binary representation of k, you can skip those many steps, the most significant and then the next to most significant, and you will reach the node in log n instead of k. So we are now doing actually log k operations instead of order of k operations. Okay, there's one more question. This question is, again, it could be solved using RMQ, but if you can come up with a bit different approach, here we are actually asking for, instead of generalizing the query thing of I to j, we keep it to I plus m, where m is fixed. So when you are solving that type of query, could you do something different? Just try exploring it. We'll discuss it tomorrow morning.
Yeah, it does in type independent manner. So basically, if something works for an integer, it also works for a character or any other data type that you define. Yeah, use any algorithm on any container. Similarly, so sort and all. For example, if you call sort, if it works for an integer, it will work for anything. The same. Yeah. So yeah. The first thing is using namespace std. As you all might know, in std there are a lot of functions defined like cout. So if you give this using namespace std first, you don't have to give always std : cout and so on. So just include using it namespace std. Also you can define your own namespace, but yeah, that you don't need now. Okay, so the first thing I'll be covering is vector int. So vector int v of 4, 10. What it does is it creates an array. A vector is basically a dynamic array. So vector int v of 4, 10 creates an array of size 4, each initialized to 10. So yeah, vector you can basically, okay, we'll see how we can dynamically change it. So v dot pushback of I, it pushes the element I. So after that operation, the size of v will change from 4 to 5 after each of these operations. So after the loop is executed, the size of v will be 10 and the elements will be 10, 10, 10, 10, 0, 1, 2, 3, 4, 5. So yeah, that's pushed back. And yeah, v dot size will give the size of the current size of the vector. So, and you can access it like v of I. So v of I will give any element. Also, another useful way of traversing the vector is for vector in colon iterator. It will return a iterator to the beginning of, that is vector in colon iterator is just the iterator which can be used for traversing, equal to v dot begin. V dot begin will give an iterator to the beginning of the vector. So, and similarly v dot end will give an iterator to one element after the end of the vector. So it equal to v dot begin, it not equal to v dot end plus it will basically traverse the whole of the vector end. Yeah, so cout star it will output the, it will output the integer currently pointed to by it, and you can update it as star it equal to minus star it or any other statement. Okay, so yeah, now we go to some of the more useful functions. So assume the vector v has many elements. Random underscore shuffle of v dot begin comma v dot end just basically gives a random permutation of this. So if you are writing randomized solutions, this may be useful, but yeah, mostly in algorithmic programming competitions you won't be using it, but anyway it's useful. So sort basically takes as its input 2 pointers. So sort v dot begin comma v dot begin plus 5 will sort the first 5 elements of the array. Reverse v dot begin v dot end will basically reverse the array. Sort v dot begin plus 5 v dot end comma my function. Now what the my function does is it defines the operator less than for the given for the array. So say if v was a structure instead of an integer. If for an integer by default the less than operator is defined, so you don't need to specify a separate my function for that. It will take the default, but you can still give the my function and it will take the take whatever is defined by the my function. But still for a structure you have to define the operator less than for sort to work. So this my function basically is a way to provide the operator less than there. I will tell you how to declare the my function later. Yeah, so v of 0 equal to minus 10 tells that you can even update by its index. Vector in w equal to v, so this basically creates a copy of the vector itself. And w of 0 equal to minus 5, this is just telling that it creates separate copies instead of copying pointers like what is done in integer arrays. Yeah, so iterator, it is a pointer customized for traversing a data structure. Yeah, we just saw how to traverse it. So iterator can be of any types, noise, okay, yeah. Dereference like a pointer. So star it will basically give the element referred to by the iterator. And yeah, this we saw increment, decrement, yeah, it plus plus, it minus minus will also work. For some data types, for some other data structures it won't work, but for vector it will work. Compare, yeah, you can even compare iterators, unlike in integer arrays where you can't basically compare pointers. And yeah, it gives the next element. So we'll talk about ranges now, ranges in STL. So the v dot, so we saw just the sort function now, sort of v dot begin comma v dot end. Basically the range v dot begin comma v dot end specifies the range to be sorted. It gives a range of elements. So it can be done using iterators or pointers. So yeah, a comma f plus 5, note the 5 there and not the 4. A pointer after the end of the index. Yeah, left, right exclusive. Yeah. So the custom function that I was talking about, in sort basically how to write the comparator. So bool my order int a comma int b, return a greater than b. This will basically sort in reverse order. So yeah, instead of that you can, for sorting in reverse order, instead of my order you can even give a greater in function. We'll see that later. But for any other structure you can tinker that my order so that it sorts either based on ascending order or descending order or whatever order you want. Okay, so we'll move on to containers now. So the container is the standard terminology used for data structure. Contains elements and provides operations. Yeah, vector, set, map, string, queue, all these are containers. Okay, so we'll see the vector updation properties. So for vector, the head is